Dear students, welcome to another session on DSP Lab. In today's lab, we'll be implementing linear convolution on the octave. We'll be writing two programs. First program will implement linear convolution with the available built-in function in the octave. And in the second program, we'll implement linear convolution by using DFT and IDFT methods. Before we start with the programming in octave, let us revisit some of the concepts to understand linear convolution. As you can see, if a system is linear time invariant system, and when you apply unit impulse function as an input to this linear time invariant system, whatever output we get, it is called as unit impulse response or unit sample response. Unit impulse response or unit sample response is the output of a linear time invariant system when unit impulse function is applied as an input to it. So unit sample response or unit impulse response is denoted by h of n. Now this unit sample response will be the characterization of a linear time invariant system, and this unit sample response is helpful to obtain the output of any linear time invariant system for arbitrary input x of n. So the method with which we obtain the output of an LTI system with the help of an impulse response for any arbitrary input is the process called as linear convolution. Okay, now as you can see in the second block diagram here, we have a linear time invariant system which is characterized by its impulse response h of n. X of n, let x of n be any arbitrary input to this linear time invariant system. So output y of n will be convolution between the input x of n and the impulse response of the system h of n. So this is the linear convolution, and this linear convolution is represented by the convolution summation mathematically as y of n equals to summation k minus infinity to plus infinity h of k x of n minus k. Now this convolution summation is commutative. You can write h of k x of n minus k or x of k h of n minus k. It doesn't matter. H of k is the unit sample response and x of n minus k is the time reversed shifted input to the linear time invariant system. Okay, so how to use this convolution summation? We understood this while studying second module of signals and systems in the fourth semester. Okay, so we had solved the problems by using graphical method as well, where we'll be placing one of the sequence as it is and another sequence will be time reversed first and then shifted towards the far left side, and then we'll keep on moving it towards the right side, and we'll note down the region where the mathematical expression remains same. Okay, and by that we'll be writing the total output y of n at the end. Now to implement this linear convolution in the octave environment, we need to understand few of the properties of this linear convolution. And the first property is length of the output of a linear time invariant system obtained by linear convolution will be length of the two sequences, sum of the length of two sequences minus 1. Okay, for example, if x of n is the input and if its length is L, if it has L number of samples in it, and let m be the length of the impulse response. If impulse response has m number of samples, then the output of linear time invariant system will be having capital N number of samples, where capital N will be equals to L plus m minus 1. Length, sum of the length of two sequences minus 1 will be the length of the output, which is obtained by using linear convolution. And the starting index of the output will be sum of the starting indices of both these sequences, input and the impulse response. Let x of n starting index be n1 and h of n's starting index be n2. Then the starting index of the output sequence y of n obtained by linear convolution will be n1 plus n2. Okay, so these two are to be satisfied. These two are to be satisfied. Let us consider an example here. Now we'll consider two sequences and we'll obtain the linear convolution of those two sequences by direct method as well as by using DFT and IDFT. First we'll numerically solve them, manually solve them here, and then we'll verify the same result by writing a program in Octave environment. So let's consider an impulse response sequence, a 2-point impulse response sequence, h of n equals to 1 and 2. And a small arrow mark between 2 represents this is the starting index, or this is the point where n will be equals to 0. If this is the origin n equals to 0, then the sample 1 will be present at n equals to minus 1. Okay, and let us consider a 3-point input sequence x of n with samples 1, 2 and 3, and again there is a small arrow mark beneath the sample 2 indicating this is the origin. This is the sample at n equals to 0. It means 1 will be at minus 1. Okay, so to obtain the linear convolution by direct method, we'll simply have to multiply these two sequences. Okay, so this is the alternate way of multiplication, and all the partial products will be added together. So one of the sequence will be written horizontally and vertically, and each sample from both the sequences will be multiplied together. So sample 1 from the impulse response with value 1 will be multiplied to all the three samples in the input sequence. So their partial product 1, 2, 3 will be written, and likewise second sample 2 will be multiplied to all the samples from the input. 2, 4, 6 will be written, and their partial products will be added diagonally. So 6, 4 plus 3, 7, 2 plus 2, 4, and the last sample will be 1. So this is the linear convolution output for these two sequences h of n and x of n. Now does this linear convolution output satisfy the length of the output sequence? So according to our theory here, the length of the output should be sum of the length of two sequences minus 1. So length of the impulse response, that is m, is equal to 2 and l is equal to 3 here. So output's length has to be 2 plus 3, 5 minus 1, 4. There are 4 number of samples in the output. So whatever the number of samples present in this output sequence is representing this output correctly in the time domain. And about the starting index of the impulse response was minus 1, and starting index of the input sequence was also minus 1. Therefore if you add those two, minus 1, the result will be minus 2. So minus 2 will be the starting index of the output sequence. It means sample value 1 in the output sequence will be at minus 2. Sample value 4 will be at minus 1, and 7 will be at n equals to 0. So therefore a small arrow mark is put beneath sample value 7 indicating this will be the sample at n equals to 0. So this is the direct method to obtain the linear convolution between two sequences. Now if we have to obtain the same output by using DFT and IDFT method, we'll have to pad appropriate number of zeros to make the output have 4 number of samples in it. Okay, or in other words, if the linear convolution output has to be represented in the time domain correctly, then the DFT should be having minimum 4 number of samples in it. Okay, we need minimum 4 samples to represent the output uniquely in the time domain. Therefore both these sequences, input sequence and the impulse response, will be 0 padded to make their lengths equal to 4. Okay, now how to do that? We did study this technique in module 1, so this will just be a recap of it. By using DFT and IDFT method, length of the input sequence L is 3 and length of the impulse response M is 2. So we should be having 4 number of samples in the output, n equals to 3 plus 2 minus 1. Now to pad or to make the length of the impulse response equals to 4, we already have two samples in it, so we'll be padding L minus 1 zeros. We'll be padding L minus 1 zeros to it to make its length equal to 4. It already has m number of samples where m is 2. To make its length equal to 4, L minus 1, L value is 3, 3 minus 1, 2 zeros will be padded to it. And likewise, to make the length of the input sequence to 4, it already have L number of samples, 3 samples in it. So we'll be padding m minus 1 zeros to it to make its length equal to 4. So after 0 padding, the input sequence will be 4-point input sequence. After 0 padding will be 1, 2, 3, 0, and 4-point impulse response sequence after 0 padding will be 1, 2, 0, 0. Now by using DFT IDFT method, we'll take 4-point DFT of these two sequences, multiply their 4-point DFTs, and then take the 4-point IDFT on that product DFT, which will give us the time domain sequence, which will be equivalent to the linear convolution in the time domain. Okay, so first let us obtain the 4-point DFT of the input sequence. We'll use the matrix method, which is easier to implement. So we'll write a 4 cross 4 twiddle factor matrix and multiply a given discrete time sequence to it. So the 4-point DFT will obtain is 6 minus 2 minus 2j, 2 minus 2 plus 2j is the 4-point DFT of the input sequence. In the same way, we'll be obtaining the 4-point DFT of the impulse response sequence, which will be 3, 1 minus 2j minus 1, 1 plus 2j. Now we'll obtain the product DFT yk by multiplying two 4-point DFTs, and the product DFT will be 18 minus 6 plus 2j minus 2 minus 6 minus 2j. Now on this 4-point product DFT, we'll apply the IDFT. So we'll write the complex conjugate of the 4 cross 4 twiddle matrix, multiply it with the DFT sequence, and divide all the results by 4. So we'll get 1, 4, 7 and 6. 1, 4, 7 and 6. Now this result is same as that, like the result what we obtained by using direct method. Okay, so this is the procedure that will be following exactly in the octave to write the program. Okay, now with this, let us go to the octave environment and look at the programs. And as usual, I have already written a program. I'll just be explaining this line by line. First, we'll see how to obtain the linear convolution by using a built-in function. Now, Octave provides us with the built-in function to obtain the two-dimensional linear convolution, and that built-in function is CONV. CONV stands for we need to pass arguments to this. It will calculate two-dimensional linear convolution between the sequences defined as arguments. Now, if you want to look at the documentation on CONV, you can just type help CONV in the command window and press enter. It will display the documentation regarding that, and you can see here CONV is a function from this file, and how to use the convolution function CONV. The It can have either two arguments or three arguments: conv a comma b, conv a comma b comma shape, where it will convolve two vectors a and b, where a and b are the coefficient vectors of two polynomials. The convolution represents the coefficient vector of the product polynomial. Okay, now the size of the result is determined by the optional shape argument. Now the third argument will be optional. Now depending on the type of output you need, you can use the third argument, but will not be using it in our program. Okay, so in this way we need to use the conv function to obtain the linear convolution between two sequences a and b. So the first thing that we need to do in our program is, let us ask the user to give two input sequences a and b. Either we can call it as input and impulse response sequence or two random sequences, and then obtain the length of those two sequences and the starting index of those two sequences, and then by using this convolution operator let us calculate the linear convolution. So coming back to the program, so first line, CLC clear the command window, clear all. If there is anything in the workspace earlier to the execution of this program, let us clear all of that as well, and then close all. If there are any additional windows open, let let us close them as well. Okay, now X, input the first sequence. It will ask the user to input a sequence, and H, input, is the built-in function to ask the user for the sequences or the input value. Enter the second sequence. Now let us determine the or obtain ask the starting indices of these two sequences and call them as XS. Input, enter the starting index of the first sequence X. HS equals to input, enter the starting index of the impulse response H. Now to display the output correctly, the starting index of both the sequences are to be added together, and the sum of the starting index of both the sequences will be the starting index of the convolution output. So we'll add those two. Ys is equal to xs plus h of s. This will be the starting index of linearly convolved sequence. And then now we'll calculate the convolution by for the two sequences and we'll store it in y. Y equals to conv of x comma h. X is the first sequence, h is the second sequence. These two are passed as an arguments to the conv function, which will calculate the linear convolution of these two and store the result in y. Now we'll display y equals to as it is because it is in the single quotes, and then display y. Now the line number 9 will display the value that is stored in this variable y. Now to represent the index value, let us define the x-axis that will be representing for each of the sequence. Let n1 be the index value for the first sequence. So starting index of the first sequence is xs. We already know that. The interval for this vector has to be 1, and the last index will be total number of samples minus 1 plus xs. So length of x minus 1 plus xs will be the end index of the first sequence, and likewise we'll be defining the other two. N2 hs, the starting index of the second sequence, colon 1 length of h minus 1 plus hs. Okay, for example, to understand this, okay, now let us say uh, in the previous example for the input sequence was having three samples 1 2 and 3, and the starting index was minus 1. So the index value for all these three samples were minus 1 0 and 1. Now let us understand how this statement will generate that. Okay, so starting index is minus 1, we all know that. Step size will be 1, and end index will be length of x. Length of x, we know that length will give us the number of samples present in that sequence. So length of x will be 3, 3 minus 1, 2, 2, xs value is minus 1, so 2 minus 1, 2 minus 1 will be 1. So in line number 10, these will be the values. So starting index will be 1, step size will be 1, ending index will also be 1. So with this, the vector generated will be 1 0 and 1 because step size is 1. So these three indices will be assigned to each of the sample value in the input sequence 1 2 and 3. So once starting index or 1's index will be -1, 2's index will be 0, and 3's index will be 1. With respect to this index value, with respect to these index values, we'll be plotting the first sequence. Now in this way, the indices for the other two sequences, that is the second sequence as well as the output, will be generated here. And to plot the multiple graphs in the same graph field, we'll use the subplot function. Subplot 311, that is, a graph field will be divided into 3 rows but a single column, and in the first graph field we'll be plotting x with respect to n1. Y label will be input sequence and title will be the input sequence. Subplot in the second row will be plotting the second sequence, that is impulse response, with respect to n2. Y label will be h of n and the title will be impulse response. And in the third row, we'll be plotting the output sequence with respect to n3. So n1, n2, n3 are the index values of the input sequence, impulse response, and the output sequence. Y label will be output y of n, x label time index n, and title will be the linear convolution. Okay, so let us run this program by clicking on this run button. When a pop-up will appear, either you can say change directory or add directory to load path. Click on add directory to load path, then go to command window. Now in the command window, you will see the first statement executed from this program, that is line number 2, which says enter the first sequence. Now remember, if you are entering a scalar value, then you can input it directly. If you are entering a vector, then it has to be enclosed within square brackets, and the sample values in the vector can be separated by either a space or a comma. So let us input 1 and 2, which is the first sequence, or if this is an input sequence, so let us input the input sequence with samples 1, 2, and 3 that we considered as an example here. Okay, after inputting the sequence, press enter. It will execute the second line. Here enter the sample values of the second sequence, which are 1 and 2. Now enter the starting index of the x. Starting index of the x that we used is -1, so I'll input -1, and the starting index of the impulse response also we considered is -1. Press enter. This will this will display the rest of the program will be executed and the output will be displayed. So ys, which is the starting index of the output, is the sum of these two starting indices of the first sequence and second sequence, so it is -2, and this is the output 1, 4, 7, and 6. 1, 4, 7, and 6 that we obtained. 1, 4, 7, and 6 the sequence. So whatever program we have written, it is correct. Now to adjust the starting indices, Octave will not do it directly. We need to adjust it. Okay, so that's why we are generating these index values n1, n2, and n3, and so on. And this is the graphical output. This is the input sequence with 3 samples. So the index of the first sample, whose amplitude is 1, is at -1. Second sample with amplitude 2 is at 0, and third sample with amplitude 3 at 1. And the impulse response sequence has 2 samples, 1 and 2, which are placed at -1 and 0. And this is the output. Third graph is the output. 1, 4, 1, 4, 7, and 6, which will be presented -2. First sample is present at -2, second sample is present at -1, third sample is present at 0, and fourth sample present at 1. So this is the starting index, 2 is the starting index, and 1 is the end index of the output. So this is how we obtain the linear convolution by using the built-in function. Now CONV is the built-in function provided by the Octave, which calculates the two-dimensional linear convolution between two sequences. Now if we need to implement the linear convolution without using this built-in function, or by using DFT and IDFT, then we'll be doing it with the help of second program here. Okay, now like I said, instead of the procedure that will follow here is the procedure in which we obtain the 4-point or n point DFT of a discrete time sequence. Okay, now instead of using this twiddle factor matrix and multiplying discrete time sequences with this and all, we can directly use FFT and IFFT command. FFT, fast Fourier transform command, calculates the 4-point DFT, 4-point DFT of the discrete time sequence that has been defined, and likewise IFFT will calculate the IDFT. But instead of doing that, let us generate a twiddle factor matrix and then multiply the discrete time sequences with it. But before that, we need to pad the zeros appropriately. So clear command window, clear all, close all, X input, enter the first sequence, H input, enter the second sequence. Now let NA be the length of X. Now NA will have 3 because there will be 3 samples in the first sequence. So length is a built-in function which calculates the number of samples in the given vector, and NB will be the length of the impulse response or the second sequence. So capital N equals to Na plus Nb minus 1. Now this will be the length of linearly convolved sequences, length of two sequences minus 1. So M will be the zero padded sequence of the first sequence X. Now how do we do that? So first the samples from the first sequence X will be retained as it is because X is having the first sequence values, so they'll be retained as it is. After that, appropriate number of zeros will be padded. Now for zero padding, we have understood what is this function, zeros function, while in the introduction class. So zeros will generate the all zero values of these dimensions. So in this case, it is the for one row but n minus 1 number of columns. Capital N is sum of two lengths minus 1. So in this case it will be 3 plus 2, 5 minus 1, 4. 4 minus Na. 4 minus Na is 3. So sorry, capital N will be 4 and Na is 3. 4 minus 3 will be 1. So zeros of 1 cross 1. So one row, one column element of 0 will be generated and it will be appended to the sequence X. And likewise, N will be the zero padded sequence of H. So we'll retain the samples from H and zeros of 1 comma N value is 4 and NB value is 2. So 4 minus 2, 2. It will be zeros of 1 comma 2. So one row, two columns of zeros will be generated by this function, and those two zeros will be appended to H. And now we'll generate an index to be used in twiddle factor matrix k equals to 0 colon capital N minus 1, where capital N will be the length of the linearly convolved sequence, and we have used this exponential function to generate the twiddle factor matrix earlier as well. So we'll define the twiddle factor value as exp exponential of minus j 2 pi k transpose k divided by n. Why it has to be transpose and all we had seen while studying the DFT program. Now to obtain the 4-point DFT, this twiddle factor matrix has to be multiplied with the zero padded sequences, and the zero padded sequences are m and n. So capital X will be the DFT of the first sequence X, which will be obtained by multiplying the sequence with the twiddle factor. Now the position of these sequences and matrix should satisfy the matrix multiplication rule. Okay, so if you write W multiplied by M, it will not work because the number of rows, number of columns in the first matrix and number of rows in the second matrix will not match. So accordingly you need to make the arrangement which we had explained or which we had gone through while studying the DFT program in Octave. Okay, you just before going to this program, you just refer to that. Then you will understand the modalities that are used, why k transpose is used, and why uh, m is multiplied with w, why not w multiplied by m and all. Okay. Likewise, the 4-point DFT of the second sequence is obtained by multiplying zero padded sequence n with the w, and then we'll obtain the product DFT capital Y as capital X dot multiplication. Dot multiplication is the bitwise operator. So first DFT point in X and first DFT point in H will be multiplied together, and so on. So capital Y will be the product DFT. Capital Y will be this sequence now. 18 minus 6 plus 2j minus 2 minus 6 minus 2j. So this will be that sequence. Now to obtain the IDFT, let us obtain the conjugate matrix. So see exp of, to make the conjugate, we'll just remove this negative sign, or you can write conjugate. You can use conj function as well, conj of w, even that will work. Okay, so c equals to exp of j 2 pi k transpose into k divided by n, and this is the IDFT formula in the matrix form. So product DFT multiplied by the conjugate matrix divided by n stem y, it will be displayed and plotted. Okay, so let us execute this. Go back to command window, enter the first sequence. First sequence is 1, 2 and 3. Press enter. Now input the second sequence. Second sequence values are 1 and 2. Press enter. All of the things will be done automatically. So you can see the zero padded sequence here. After executing line number 7, the first sequence will be zero padded. First 1, 2, 3 are as it is. 4 minus 3, 1, 0 is padded to it. And after line number 8, we'll get the zero padded sequence of the second. That is 1, 2 will be retained as it is. 4 minus 2, 2 zeros will be padded to make its length equal to 4. So capital X is the 4-point DFT of the first sequence, which is 6 minus 2 minus 2j, 2 minus 2 plus 2j. You can verify that result here as well. 6 minus 2 minus 2j, 2 minus 2 plus 2j. And capital H is the 4-point DFT of the second sequence, which is 3, 1 minus 2j minus 1, 1 plus 2j. And the product DFT is 18 minus 6 plus 2j minus 2 minus 6 minus 2j. And its IDFT of this, which is the linear convolution, is 1, 4, 7 and 6. Even though these are real values, they are represented in a complex way, but the imaginary part is 0, so they are just the integer values. This is how the octave represents the numbers, even the uh, real numbers, by making the imaginary part as 0. So 1, 4, 7 and 6, the same result has been plotted here. 1, 4, 7 and 6. Now we did not worry about keeping this index right. We can include the steps from the first program here as well to make that index right and all. Okay, so these are the two programs using which we'll be implementing linear convolution in the octave by using the built-in function and the DFT and IDFT method. I hope you all followed these two programs. Try to implement them, and if you face any difficulty, let me know. Thank you.